Okay, great. This will be a kind of extended talk with a lot of demos and some live demos as well with some coding. When I will walk you through what is the current research, what methods we have for essentially state-of-the-art code obfuscation methodologies, which leverage transformation on expressions combining both arithmetic and Boolean expressions. Okay, let's talk about it today. First of all, if you want to follow your slides directly, they're already uploaded, as well as all the materials in this repository. So you just scan this QR, you got the slides immediately, the same slides that I'm using in case you find it more comfortable to look at them on your devices. Okay, it's just my GitHub repo talks, and you just navigate to 2022 Hack in the Box. You have already the slides available. Just a little bit about me, very, very briefly. I'm a hacker. I've been doing reverse engineering. I'm also a mathematician. I work doing stuff for a company, and I'm also doing research and trainings with Fura Labs, which is my own security firm. Okay, so here you have also some links that you can follow me around Twitter, both on my personal account and also Fura Labs account. Okay. So first a warning, this talk, this presentation may contain and actually will contain a little bit of math, not that much, but I will use some math to explain the basics of MBA transformations and also, well, some assembly code, very, very simple, but if you're not very used to, I warn you that there will be a little bit of assembly code, but very simple, and we will go over it if it's necessary. This will be a little bit of the agenda for today. First, I want to give you a little bit of context of where we placed when we talk about code obfuscation. So I want to contextualize that in general and see where our techniques and the research that is being done with mixed Boolean-Arithmetic transformation, how does it fit within this broader context of code obfuscation. Then we'll discuss a little bit about MBAs. We'll see some introduction, motivation, discuss a little bit about differences between use of this kind of expression, difference between obfuscation and also cryptography that might as well use combined operators from arithmetic and Boolean fields as well, and then give some definitions for the kind of objects that we will be dealing today, essentially polynomial MBA expressions and also a subset for them called linear MBA expression. Finally, we will present some techniques that, leveraging these tools that we have with MBA expressions, allow us to obfuscate code. Essentially, both obfuscate expressions that translate to obfuscated instructions, but also obfuscating constants themselves. We will also motivate a little bit this kind of obfuscation of constants, why we might be interested in that. So let's talk first a little bit about code obfuscation and the context about code obfuscation. And essentially, code obfuscation is one of the technical techniques or technical protections that we have against what we call man-at-the-end attacks, which is a scenario where the attacker or the analyst, depending on where you put your moral boundaries, is such that it has a control over both the binary that it's analyzing, usually a binary program, the code that is analyzing, and also the environment where this program or this code is being run. Okay, this is the scenario of a man-at-the-end attacks. And within this broader scenario, we find different categories of protections. Mostly, we can differentiate legal protections and technical protections. We won't talk anything about legal protections today, but they are in there. So if doing some kind of man-at-the-end analysis, you might face some legal lawsuit. So that might be something to take into account before doing that research or before at least doing it public. We will center specifically on the technical protections, and more in concrete, we'll take a look at obfuscation, which is, as you can see, it lays a little bit in the same level as other kinds of protections that we could implement to protect our software, our code in such a scenario. We have our techniques such as encryption, also server-side execution, so we make the execution of sensitive parts of our code to not be executed within the client, within the environment and the actual code that the attacker controls, but on a an external server that is from our control. Also, the recent trusted native code platforms that are becoming more and more common nowadays. So these are a bit the great context where obfuscation lays. So I really want you to understand that obfuscation is just one of the technical protections. It can be very advanced protection and very, very used around for software protection within the context of this kind of attacks, this kind of scenarios. So what is code obfuscation about? Essentially and very, very broadly, it's a transformation process that taking as an input for this transformation process an initial program P or some code, we will want to transform it into a program P prime, let's call it, or another code which is functionally equivalent, which behaves in the same way from a semantic point of view. But this transformed code, we want it to be way harder to analyze it and way harder to extract information from it than from the original code or the original program, okay? The motivation essentially is usually we would like to prevent reverse engineering, but if you have some experience around reverse engineering, you know that you never can prevent it like 100%. What you can do is complicate it to a level where your adversary would have to waste so much resources, both in time and like full-time employees working towards reverse engineering something that at some point it's not worth for them. It will waste so many time resources, different kind of resources that it makes it so not worth to do that. So we wanna actually what we can do with obfuscation is complicating this process. Okay, we will never prevent it like at all against a sufficiently motivated actor with infinite time and infinite resources. But then here it also plays a role your threat modeling. Okay, so you really need to have a concrete threat model to decide to which degree you want to obfuscate, you want to protect your software. Okay. Then what is the presence of this kind of protection, this kind of software obfuscation transformations? Essentially, we can differentiate two different big fields for the prevalence of code obfuscation. The first part, we can think of software protection, which is everything that has to do with intellectual property, protection of intellectual property algorithms or some algorithms that have been patented or are part of some proprietary software that the algorithm themselves is an important part of the intellectual property for the company or for some kind of researchers. So obfuscation might get in place to make the extraction, the understanding, or even the reconstruction of such algorithm or such procedure to make it way harder. Also, any kind of digital rights management, which, as I assume many of you will know, is this super fancy protection schemes that make that essentially any digital content that you buy is not yours, because then it gets tied to the platform where you buy it. Think of any kind of Netflix movies, ebooks on Amazon, on a Kindle. All of them come with DRM, which is a way of tying the content, the digital content, to the platform or to a concrete account, so you don't really own the content. And a lot of the protections, the copy protections, are kind of protections for assuring that you cannot move these files, digital content around. Need to use a lot of like dirty tricks, which are actually embedded within the source of the programs themselves, which is the scenario that we have described. So they use a lot of obfuscation to protect against reverse engineers, understanding, and in an ultimate manner, breaking, in some sense, DRM scheme, so they could recover the property of their digital contents. And also extremely popular nowadays with everything that has to do with cheating, anti-cheating worlds. If you have walked around the anti-cheating forums or even cheating discourse around, there is a lot of obfuscation present in combination with other kinds of anti-reverse engineering, anti-virtual machine, anti-debuggers, anti-analyzers, whatever. And think, for example, of those super fancy kernel drivers that you have to be forced to install to play Valorant or to play Genshin Impact or those kinds of super fancy modern and cool games. If you have just tried to load one of those drivers into IDA, into your favorite disassembler, you will see a lot of garbage that you don't understand. In the first place, because they are implementing a lot of protections against analysis, against running them, against debugging them, against the disassemblers themselves, but also they use a lot of obfuscation, really a lot of obfuscation. So, for two different purposes, I would say. On one side, you really want your anti-cheating kernel driver to not be easy to understand, especially making it not easy to leverage it or bypass it from the point of view of the cheaters, or even leverage it for doing, well, you have a kernel driver with kernel access, so you have some bugs or some way of interacting with it kind of easily, then bad things happen. Actually, really recently, I think yesterday, there was some news about some problem of some malware dropping the Genshin Impact kernel driver to load some of its code and with kernel permission. So, yeah, anti-cheating products use a lot of obfuscation to make it way hard, especially for cheaters to understand the games, and also not only in the specific anti-cheating components, but also within the games themselves. So making some parts of the games run in a way that is very difficult to understand, that is super obfuscated, so an attacker analyst has a really hard time trying to reverse engineering to understanding what's happening. That slows a lot of the process and makes the attackers, the cheaters, to have to invest a lot of resources, a lot of time into understanding that code, so they can ultimately try to build some kind of cheat around it. Okay, so within the anti-cheating cheating world, there is a lot of obfuscation, and also in the other way around, cheats out there implement also a lot of obfuscation. So companies, gaming companies working on anti-cheating, they have to spend a lot of resources understanding the cheats themselves to understand the problems that are affecting them. So it's a two-way sword in that sense. The other very, very popular scenario where software obfuscation is present is, of course, malware threats. All kinds of different obfuscation. And essentially the motivation on one hand is, at some point, we want to avoid automatic signature detection. So if we are doing some kind of obfuscation transformation, even if it's not very complicated, if we are actually changing the structure of the code or even the instructions themselves to something different, then we can bypass the automatic signature generation for our samples on a given campaign, for example. But in general, they are this kind of not that big right now, because most antivirus products or EDRs or whatever, they don't really rely on signatures, static signatures anymore. They analyze for behavioral analysis of the samples out there. So really, it's a lot more for slowing down the analysis of the samples of the campaigns, which means usually more time there are campaigns active, which usually translates to more money through whatever the means that they are making the money with a malware campaign, the malware actors. What is the super, in a nutshell, the methodology in big words of obfuscation? So you want to apply a transformation, some kind of transformation to the program, to the code, that messes, that complicates both the control flow and the data flow of the program. The control flow is essentially the way in which all the control structures of our program are related to each other. Think of all the branching condition or the looping conditions. If you have opened any disassemble the control flow graph, the graph view of a function, that's the representation of the control flow if you're giving a function. So we want to mess with that control flow, and also a data flow. Data flow is a way of representing what is the flow, what is the path that the data is taking, where some variables are declared, where they are used, where they are updated through the code themselves across the same function or different functions. So we want to mess to complicate both the control flow and the data flow of a program, and we can do that at different abstraction levels. Okay, different abstraction levels that we could introduce obfuscation could be, for example, directly in a source code. We could place obfuscation transformation directly in the source code. This is very visual. Usually, then you need some kind of control over the compilers in order to, hey, don't optimize that, or don't touch this thing that I did it on purpose, so don't touch it. But you can do that on source code. There are some tools around there that actually produce obfuscation on source code. For example, VM Protect is a widely known obfuscator based on virtual machine obfuscation. We will see a little bit on the demos about virtual machine obfuscation, and it works on source code. Okay, you just implement some directives on your C or C++ files to include it. Then obfuscation can also work on compiled binaries themselves. You just get your compiled binary and apply obfuscation in them. This is, on one hand, the best way of having really concrete control of what will end up being in the binary, because you're modifying the binary itself. But then it might be also, you need some engineering work, some thinking process, because if you're modifying a binary by itself, then probably you're modifying the offsets and the references of everything, and you would need, of course, to update the header of the binary, but also probably reconstruct all the relative references within the code itself. And if that code is called, for example, a library used by other code, you might need to fix also the offsets for the functions exported and things like that. But it's definitely possible, and there are products out there. Not as much products, at least publicly, but there are private products, software protectors that do exactly that. They work on the compiled binaries. And then we could also work on intermediate representations. And if you have done any kind of compiling with CLang, you might be familiar with LLVM, intermediate representation, for example. There are a lot of them, but this is quite known. And this is, in this sense, for example, for LLVM intermediate representation, it's quite common to perform obfuscation at that step, because then you have your compiler, like the first step on a compiling pipeline, just translating the source code to LLVM, and then in the same way in LLVM that you would apply optimization passes, for example, you could perform your own custom obfuscation passes within the LLVM bitcode directly, and then this gets translated, it gets compiled back to any native architecture that you would want to do, okay? So we have a transformation that complicates, messes about the control flow and data flow at different abstraction levels that we have discussed, and they also can affect different target units. When target units can be, well, we could obfuscate the whole program, which is not something very usual to see, just plugging a whole program and then obfuscate it in some way, but definitely you can, for example, transform an entire program into a virtualized obfuscation implementation. But what is more common is usually obfuscate a function or a set of functions, or even some basic blocks, or even some instruction or some basic operations. So it's very complicated to understand just for taking a look at it, or even within a dynamic analysis if you are not very, very certain of what you're looking at, making it very difficult to understand, okay? So we can target different target units, either on the source code, on a compiled binary, on an intermediate representation, and that will mess around with the control flow and the data flow of the programs. So just a quick remark in here, there are a lot of obfuscation techniques, okay? A lot of them. You can come up with something new that might be a new obfuscation technique, okay? Or a combination of them. What I usually like to mention is that sometimes you read of some obfuscation techniques which you might think, well, this is, okay, it's a clever trick, but it's not very hard to spot or even to revert it back. But usually obfuscation schemes can be used combined with an arbitrary number of different obfuscation schemes being combined in different orders interleaved, which means that many times you can use several weak obfuscation, transformation obfuscation techniques, but you end up the combination of them with a certain order and certain amount of them, you end up with a very strong protection from the point of view of making the program understandable or easy to analyze, extract information, okay? So, having talked a little bit about the context on software protection, code obfuscation, let's discuss a little bit about MBAs. This will be a part where at some points there will be a little bit of math, but we will go over it. We have plenty of time to discuss it. It won't be very complex, and everything will be explained and translated into C and Python, assembly, whatever. Okay, so don't worry about it. Basically, an MBA expression, a mixed Boolean-Arithmetic expression, as the name suggests, is just an expression, an algebraic expression. And if the word algebraic confuses you, just forget about it. It's just an expression which is, as the name suggests, composed by both integer operations, integer arithmetic operators, essentially additions, subtraction, multiplication, but also bitwise or Boolean operators. I will use Boolean and bitwise in an interchangeably manner, okay? Here we have, for example, AND or XOR and NOT. Okay, if you're not familiar with like formal notation for this kind of operators, this is your usual AND, this is your usual OR, this is your XOR, and this is your NOT, your negation. Okay. So this is a very simple example of mixed Boolean arithmetic expression. This is just an expression, a very simple expression that combines operators both from arithmetic, integer of arithmetics, for example, the addition, and also the implicit multiplication in here, but also bitwise operators, Boolean operators, this XOR, and also this AND. Okay, so this is very simple mixed Boolean arithmetic expression, just for you to get a sense of what does it look like in general. So MBA expressions, we can leverage them to obfuscate mainly the data flow of the code, but then we will see in the demos that by obfuscating the data flow, we bring new opportunities to also obfuscate control flow. We'll see that in the demos in a second. The essential, the basic way of doing that is applying rewrite rules and insertion of identities, essentially some kind of transformation that we will discuss in a second, to a given expression. Given we have an initial kind of simple expression or non-obfuscated expression, we apply some transformation processes that will transform this expression into another expression, another MBA expression, which will be way more complex from a syntactic point of view, from the point of view of writing it, from the point of view of the amount and the complexity of the instructions, of the assembly instructions, if you want to think it that way, that it will get translated into. But what is really important is that we want to preserve the semantic behavior. Semantic behavior means that the obfuscated expression, the obfuscated resulting code will produce exactly the same behavior. That is, given the same set of inputs, it will produce always the same output as the original non-obfuscated simple expression. That's the whole idea behind obfuscation. We want to preserve the semantic behavior of our obfuscated counterparts. Why can we do that? What is the, roughly the motivation that we are interested in doing that, and it makes sense to do this kind of transformations? Essentially, sometimes I'm a little bit too rough to researchers themselves, but essentially it's because we don't have any idea how these things work. So we are very ignorant in this field. We've been using computers which have an arithmetic logic unit for decades, and we don't really know the expressions that come from that, how they actually work. So we don't have really a way of reasoning about mixed Boolean arithmetic algebraic expressions in general. When we introduce this mixing of operators, then they do not interact well in the sense that we lose general distributivity, associativity, even factorization, which is a way of kind of separating the expressions into things that we can reason about separately. Or in general, any theory that allows us to deal with this mixing of operators as we have extensively developed for arithmetic expressions, normal arithmetic expressions, or even for Boolean expressions. We have a lot of tools and theory developed and methods to develop to work with them. So when we are mixing both of these kind of operators, then we enter to a place, to some mathematical structures about which we don't really know how they work. We are very ignorant still about them. And they are very hard to deal, actually. So just a few words before continuing, because some of you might be thinking, yeah, but isn't that kind of mixing of operators kind of the same that happens in cryptography? Like in a crypto system definition, you usually getting some input and then mixing it together in different ways using both operators from arithmetic world and both Boolean operators to produce the output, to produce whatever the resulting crypto system is, a hash function or any symmetric encryption, asymmetric encryption, or whatever. So yeah, in a sense, you're using the same kind of basic blocks in the sense of arithmetic operators and Boolean operators. But first, an historic note, the term of MBAs, of mixed Boolean arithmetic, algebra and expressions came from obfuscation research. Okay, in cryptography, they usually don't use this term at all. So if you read something about MBA expressions, usually it's within the context of obfuscation because the term itself has been introduced and has been mainly, and I would say only used within this context. But going to the actual differences, to the actual, the difference between cryptography and obfuscation with the use of this kind of expressions, this kind of mixing of operators, we would say that in cryptography, the MBA expressions that result from the application of the crypto system description or from the crypto algorithm for the hashing algorithm are in a way intended to verify that they are hard, they are complex from a semantic point of view, from a black box point of view, from the point of view of throwing some inputs, of taking a look at the outputs, and the semantics that can describe this relationship, we want them to be very hard. And by very hard, we mean that we want them not to be invertible. Okay, otherwise cryptography would make no sense. So in a sense, the complex way of writing these crypto system definitions, these algorithms, these cryptographic algorithms that can combine operations from both arithmetics, integral arithmetics, and Boolean operators, is kind of directly related with an intrinsic semantic complexity, computational complexity of the output of the crypto system, of the result of the application of this expression. So, in a summary, in cryptography, a complex syntax, that means the complex way of writing the expressions themselves, is directly related with a complexity in the semantics, in the behavior that we want to obtain. Whereas in obfuscation, what we are doing actually is starting from a simple expression, from an expression that has very simple semantics. We want to complicate it, we want to mess around, we want to produce a transformation that gives us an obfuscated expression, a very complex expression from the point of view of the syntax, from the point of view of the form of writing them, but instead of being related to also a very complex semantic, as this was the case in cryptography, actually we are expecting and we are building them so that the semantics that are related to the complex form of writing are actually very simple. That's the whole point of our obfuscation of simple expressions. We want to preserve these semantics, are kind of simple semantics, but we want to present that in a way that is very complex to deal with from a syntactic point of view, from the point of view of looking at the expressions, looking at the code generated from that, okay? Needless to say, but we'll be focusing during this session, and also my research in general with MBAs is always within the context of software protection, and in particular code obfuscation, code deobfuscation, okay? So we won't be talking a lot about cryptography in the sense, but I want to make that distinction because it's important to keep in mind, especially if you just have laying around, okay, but aren't those kind of expressions the same as in cryptography? Yes, but not for the same purpose and not used in the same way, okay? So let's start with some definitions. I deliberately decided to put the definitions of MBA expressions in a constructive way. And I mean in a way of just describing explicitly what are the basic blocks, what are the different kind of operators, and in which ways we combine them, instead of giving a more formal definition that exists. But, well, side note, I'm not super happy about that definition. I don't think this is the best definition. So also for our practical standpoint and for the purpose of obfuscation, the obfuscation, just defining MBA expressions in terms of describing the different operators that they get combined together and in which way they get combined together will be more than enough and a little bit more simple to understand in this sense. We usually, when doing research on all the research articles on literature, which is very scarce, so there is not a lot of that, we find two main categorization for MBA expressions. Namely, we have linear MBA expressions, which are actually a subset of polynomial MBA expressions. So we'll now define a little bit of polynomial MBA expressions, which will be probably the hardest slide in the whole session, but we'll go over it very slowly. And then linear MBA expressions are just a particular case of the polynomial ones. And you might be thinking, why are you giving me these definitions? I can just scurry around with understanding that we have expressions that mix integral arithmetic and Boolean operators. And for the most part, in practice, you can carry around with that. But this is kind of a niche talk, if you want. And there is a lot of research to be done, and very few research that has been already done on that. And if you try to, get interested in that and then try to go read anything about it, you will need these definitions like 100%. And understanding them from a very, 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 very compact paper is way more complex than with me going over it with colors and everything that we'll see in a second, okay? So you can be prepared to go and do your research on your own, and do not fear to read any research paper, any research article that might be in the topic because of notation, let's say. So let's start with this fancy slide for defining polynomial MBA expressions, and I will use kind of color codes mapping with this very simplified definition with a formulation with an example, so you can match it visually, and also I'll walk you through that anyways. So we said that polynomial MBA expression is just a sum of terms, and here if you know what a polynomial is in maths, normal maths, arithmetic maths, then it is very related. So you have a sum of terms, then each term is composed by a constant. In this case, an n-bit constant is just a constant on a number of bits, on some bit size. And each of the terms is this constant times the product of several bitwise expressions, okay? In arithmetic polynomials, this would be a sum of terms for an integer constant times some incognite, some x, or x squared, or x whatever. In this case, we have sum of terms, each one composed by an n-bit constant times the product of several bitwise expressions on any number of variables that we have the expression in. This is what the formula looks like. Don't be scared. You can map like all the colors to the formula itself and also to this example, which is a bit large, not so much in the sense of obfuscation, but maybe for an example is a little bit large, but I did on purpose to match everything in there. So let's walk over it very quickly. So we have polynomial MBA expression is just sum of terms. This is the sum symbol, and this we have here a sum of terms. This is the first term, sum the second term, and a sum the third term. So we have a sum of terms. In this case, 3 terms. Then each term is composed by an n-bit constant. Let's locate this n-bit constant. The formula is just the a sub I, and this subindex is just a fancy notation, math notation to say, hey, this is tied to a particular term of the expression. So this would be the a sub 1 is tied to the first term, to the term number 1 of the expression. So a sub 1, the first constant here will be 43. In this case would be 2, and this case would be 1 to 3. Okay, this is the constant. And then the rest of it is just a product of bitwise expression. So here we have a product of different bitwise expression. In this case we have 3 bitwise expressions because the first one is x and y or z. The second one is exactly the same. This is why it is squared. And the third one is x or y and z or t. These are a product of several bitwise expressions. How many bitwise expressions in this case? We have 3. We have this first one, the same repeated, this goes over the square, and then this other one. And then a number t of variables, which mean, okay, how many variables are we using to generate these expressions? How many inputs we will have in this MBA expression? In the second case, it's very, very simple because we have a several bitwise expression. In this case, several means just only one bitwise expression, and the bitwise expression that we have is just x, which is the constant, which is the variable itself. Okay? We have all the color mappings in here also for mapping the definition, the formula, and the example. In the third case, we have this is the everything at the right of the 1 to 3 is the product of bitwise expressions. In this case, we have 4 bitwise expressions. The first one is x or y, the second one is z, and the third is t, and the fourth is t as well. That's why we have t squared. Okay? So this is essentially the definition of a polynomial MBA expression is, okay, we have a polynomial, but instead of having like single variables being multiplied by a constant and added together, which is a normal polynomial, if you want to say it that way. In this case, our variables are actually bitwise expressions that can end up being multiplied by themselves. So this is, let's go again. This is a sum of terms. This is the sum. We have here the sum of terms, 3 terms being summed together. Each one is composed by an n-bit constant. So this is the constant tied to each one of the terms. And each of the terms is the constant times a product of several bitwise expressions. So we have a product of several bitwise expression, one bitwise expression, the second one, the third one, and so on and so forth. Okay? If you have been a bit lost in here or you didn't get it 100%, don't worry. You have already the slides. You can check it out. And for the practice part, you don't really need to remember this definition at all. Okay? You can just remember it's a mixing of operators. But I really wanted to do this so you can go out and read anything about MBAs and understand and be able to face whatever comes next and whatever formalization we have from that. Now, when we have seen that, then defining a linear MBA expression is very easy. It's very easy and it's way more simple. But I want to define first the polynomial, because then the linear MBA is just a particular case. It's just the case in which we only have one bitwise expression. Okay, so we could represent it in that way, which is, if you compare that to the previous one, the only thing that we are ditching is this product of bitwise expression. Why? Because we are defining linear MBA expressions in a way of restricting our expressions to those that only have a single bitwise expression. Okay, so we impose that restriction and call it linear MBAs. In practice, here, side note, anywhere that you go around and read about something that's linear, you can in practice think of it vaguely as a restriction that you're imposing that will not allow variables to end up being multiplied together. Okay? This is a very vague definition, and if there is some mathematician in the room, might jump onto me, but for practice, in practice, you can vaguely think of linearity or whatever it might apply, any kind of expressions, any kind of thing that you're reading about and mentions, hey, this is a linear transformation, this is some, it's preserved linearity. It means that we don't allow variables to end up being multiplied together. And then this makes a lot of sense if you want to think it a little bit geometrically, because as long as you only have one variable, what you have defined are lines. And at the moment that you just allow for variables to be multiplied together, then you start to have curves and other kind of surfaces on any dimensional space, okay? So just side note, linearity is essentially we don't allow variables end up being multiplied together. In here, by the means of just allowing a single bitwise expression, we don't allow the possibility that different bitwise expressions and finally variables end up being multiplied together, okay? This is an example, which is the very same example that we saw at the beginning. Is actually a linear MBA expression. Why? Because we just have a sum of two terms in this case. The first term is composed by a constant, which is 1. It's implicit in here, times a single bitwise expression. In this case, the bitwise expression is x or y. The second term, the constant is 2, and the single bitwise expression that we allow is x and y. Okay? So this is an example of a linear MBA. You might be also wondering, why do we even need those kinds of definitions? And the answer is because we don't know anything about MBAs, and by trying to put names to different ways of expressing things in a kind of general way, then we can start working with these mathematical structures, these mathematical constructs, in a kind of formal way and deriving knowledge from it, okay? And then there are some fancy things, as any kind of MBA can be expressed as a combination of polynomial MBAs and other things. So we understand polynomial MBAs, which we don't yet fully, or at least decently enough from my perspective, then we kind of understand everything that we can construct with MBAs. Okay, so let's move a bit onto motivation and a little bit of obfuscation. How does it play a role in here, obfuscation? How do we plug the obfuscation thing that we have been talking, leveraging these kind of MBA expressions, MBA transformations actually. So notice, for example, that this example that we have been seeing a couple times already, this is an MBA expression which actually simplifies to this other expression, which means this expression and this other expression, which is just the addition of two variables, are semantically equivalent. In other words, if we plug any x and y inputs to this expression, it will always give us as an output x plus y. From a semantic point of view, from an input-output relationship, this expression produces the same behavior that this other expression, which is just an addition of two variables. So we say that the expression is a more complex expression than the is-emp from a syntactic point of view, from the point of view of writing them, but they are semantically equivalent. From the semantic point of view, from the point of view of its behavior, its input-output relationship, they are equivalent. we can actually verify very easily that they are equivalent. We can plug an SMT solver. We won't talk a lot about SMT solvers, but we just will use them to prove semantic equivalence. In case you don't really know what an SMT solver is, you can treat this as a magic black box that can answer hard questions for us. And in this case, we can solve constraints. So we can ask the SMT solver, hey, here you have these constraints. Is this possible to happen? And if it's possible, can you give me an example where this is the case? And leveraging that, SMT solvers are able to produce proofs of semantic equivalence. We can directly ask an SMT solver, hey, can you prove that these two expressions are semantically equivalent? That is, that they are exactly producing the same behavior all the time. So these are some super simple Python code. If you have checked out the repository, I will also link at the end of the talk. But you have all those demos, all the code that appears in here, you have all those demos in there, okay? Within the same name appearing here. So we just import everything from Z3, which is the SMT solver that we will be using. And we just say, okay, let's define X and Y as bit vectors of 8 bits, 8-bit variables, okay? Within the context of Z3 objects, let's define 8-bit vectors, 8-bit variables, sorry. And then just define these two expressions that we saw, the first one, the second one, and we ask this SMT solver, hey, prove me the semantic equivalence between these two expressions, okay? We just run it, and it's very, very quick to prove that. Okay, so let's talk a bit now. We have this motivation, like how do we leverage MBA transformations to obfuscate, to actually produce obfuscation transformations. So the previous example that we have just seen, like these two different representations for the same semantic behavior, for the same addition semantics, if you want, this suggests a basic obfuscation idea, which might seem really dumb but works really well, which is, okay, let's just, any place in our code that we want to obfuscate that an addition is present, let's just replace that addition by this other expression involving XOR and AND Boolean operators. So this way we could have the same code from a semantic point of view, but we will change its syntactics, we will change the form of writing, and at the end, the complexity of the instructions that will result from this code, okay? So, to put it in nice words, the idea for obfuscating with MBA transformation is giving an initial expression, initial MBA expression, very simple, that describes the semantics that we want to obfuscate, that we want to hide. Let's call it E1. What we're interested in doing is generating a second expression, E2, which is semantically equivalent, which is equivalent from the point of view of its behavior, from the point of view of its input-output relationship, is semantically equivalent, but this E2 has to be syntactically more complex. It has to be more complex from the point of view of its writing form, its syntactic representation, okay? This process to construct this kind of transformation usually rely on two differentiated components, two differentiated techniques that we have. And we can use them either alone or combined without any problem. Those are called, MBA rewriting and also insertion of identities. And we'll talk a little bit about both of them. Very, very simple ideas, but very powerful as well. So with MBA rewriting, the whole idea is that we choose an operator or even a sub-expression if you want, and then we just rewrite it in an equivalent MBA expression, okay? From the example that we saw before, this is the idea we have discussed. So when we see some addition in the code that we are trying to obfuscate, the expression that we are trying to obfuscate, we will replace that by this other expression, which is, as we have been saying, semantically equivalent but more complex from the syntactic point of view. What is really cool in here, and a lot of people don't really get to play with that, is that kind of sign out polynomial MBAs, and in particular linear MBAs, which are polynomial MBAs, have a really nice property, which is composition, which essentially means that you can plug in here in X and Y can be also sub-expressions. They don't need to be single variables, which means that you can apply these rewrite rules iteratively and grow the expression really, really fast. Because now this very same rewrite rule, we can apply it to this resulting expression. We just use this X or Y as our X and this 2 times X and Y as our Y, and we can apply the same rewrite rule. but now with that part being x, that part being y, and we just expand the resulting expression, okay? This is a fancy property of polynomial MBAs that is composition, actually, that we can apply any transformation not only to single variables, but to sub-expressions themselves, and it will work exactly in the same way. Let's talk about insertion of identities, which is another way of producing such obfuscated or more complex expression from my initial one. And the idea is having an expression or a sub-expression that we want to obfuscate, that we want to transform into something more complex, and then we need a couple of inverse functions on the bit size that we are dealing with, okay? These functions usually are affine functions, and an affine function is, again, vague note, but it's some function in this form. It's just a linear function because we don't have variables end up being multiplied together, which has this form. It's just a constant times whatever the input might be a variable, might be an expression, whatever, plus another constant. So you want to think of that geometrically if you want. The only thing we are doing is shrinking or expanding our variable and then moving it around. It's just this multiplication by a constant and then moving it around. Those are called affine functions. Here I also like to mention that I put this as affine function, and I say that it's often affine functions because if you go to research literature, you will find like almost exclusively affine functions used there. There is no reason. There is no hard reason why they have to be affine functions. Any inverse mapping, any pair of inverse functions will work. It's just, well, people doesn't really read well the research or don't understand it well. They just go to the first paper, they use affine functions, then everyone else is using affine functions. But there is no hard reason why they need to be affine functions. Any inverse mapping, any inverse pair of functions, either affine or whatever kind of invertible mappings on m bits will work exactly in the same way, okay? So the idea is we get our expression that we want to obfuscate, and then we have a pair of invertible functions, and we apply the first function to the expression, and then the other function to the expression. You might be thinking, well, but if I apply two different functions which are inverse to an input, then I get exactly the same. And that is the whole point from a semantic point of view. But if you are doing that, expanding the symbolic expression that you obtain, then you're making it bigger and bigger, you're growing it. We're going to see an example right in the next slide so you understand what I mean by replacing symbolically and then expanding, like writing actually the content from that. Let's see an example so it will clarify a lot of things from these two techniques. Let's just, again, start with our very, very simple expression, x plus y, and consider the following functions, which are affine functions in this case, on 8 bits. So these functions are inverse, which is a function. The first one just maps x to 39x plus 23, and the inverse function maps 151x to 111. These two functions are inverse functions, actually affine inverse mappings on 8 bits. So we have our expression that we want to obfuscate and the two functions. The first thing that we're going to do is, well, let's consider e sub 2, which is obtained by applying the previous rewrite rule. So this is like the first obfuscation step using a rewrite rule. Using the rewrite rule that we saw where this addition can be expressed also semantically as that. We have this rewrite rule. This is exactly the rewrite rule that we saw in here, okay? So first of all, we apply the rewrite rule, and we obtain e sub 2. And then to this expression, we will apply the insertion of identities. Let's do it in 2 steps. First, we apply the first function, and the only thing that we do is just apply the definition of the function. We apply the function to e sub 2, which is 39 times e sub 2 plus 23. We call it etemp, temporally, okay? Now we apply the inverse of the function. We need to apply the inverse to the original function to the expression. So we just apply it to the etemp, which is exactly that. And what do we get? Well, just apply the definition of the inverse function, 151 times etemp plus 111. And now we expand this. Expanding, I mean, okay, but let's just replace etemp, but whatever is in here. And then now let's just replace e sub 2, but whatever is in here. So we obtain the final expression. And if we do that, we get E3, and we observe that essentially we have 151 times E10 plus 111. So this is the 151, this is the 111, this is everything else, the E10, and the E10 check that this is 39 times E sub 2 plus 23. 39 times E sub 2 plus 23. So when we are expanding it, we are applying to functions which are inverses, but as we are not evaluating a concrete expression, but we are constructing the symbolic expression from it, we are expanding it, we arrive to a more complex expression, okay? Now, for now you have had to trust me that these things work and are correct, but we can actually prove that. So very practical demo in here. Let's just consider the three expressions that we have seen. This is the first original non-obfuscated expression. This is the expression obtained through the insertion of through the application of the rewrite rule that we saw. And then this is the expression that we obtain by applying the function identities to the second expression, okay? This is the three expressions that we saw in the process. What we will do first is, well, compare the syntactic complexity of them. You don't really have to do a lot of work. You can already see that within the way of writing them as expressions. But let's take a look at that, how it would translate to assembly, for example. Then we'll observe the semantic equivalence of the three expressions by observing, let's say, okay, let's just implement these functions and see that they produce the same input-output behavior. And finally, in this case, we will prove, we not only observe that, but we will prove that they are semantically equivalent with the help of an SMT solver, okay? So first thing, let's just compare the syntactic complexity of the three expressions. And very, very simple. It's just observational exercise. This is just the expression put in C, and this is the assembly, the produced assembly, well, minus the function prologue and the functional epilogue, okay? So the actual assembly code doing the expression works like that. If you're reversing anything, you have a function that you just see that, then it's immediate, it's an addition. If you see that, well, it's not that complicated. You may need a little bit of pen and paper, but you can see quite easily that this actually corresponds to an addition because, well, some tricks on how this is actually working on the XOR and the carry values with that. But then if you see that, or this representation, it's very improbable that you understand what's happening in there, okay? And again, those are very, 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 very limited and simple examples. This expression can grow as big as you want, like bigger than the whole screen, if you want, okay? Because we can produce this rewriting and insertion of identities iteratively, and it grows really fast, especially when you plug in sub-expressions into the rewrite rules. This grows really, really fast, really, really quick into something really big, if you want to do that. So the degree of obfuscation of the resulting expression is totally arbitrary. Now let's observe the semantic equivalence between them. In this case, just, well, some fancy C code. I define the three functions of them. Then I get a couple inputs from standard input, and then I just call the three functions, okay? There's nothing fancy in there. You also have this code, but just defining the three functions and calling them with inputs from the calling. Just call, okay, copilot, let's call the program with 1 and 2, and you will see that all the three functions produce the same semantic behavior, and the same for this example. They produce the same output. This means they are producing the same input-output burst. But in this case, we are just observing that. We can actually prove it. So let's just prove it. We're going to prove this diagram of equivalences, which is a way of proving when we want to prove that a lot of things are equivalent between themselves. The naive approach is just proving one with everything else and the second with everything else, but it's just a waste of time because we can prove like the whole circle, then you can go from one to the other and you don't need to prove all with all, okay? Actually, the last one is not even necessary because the equivalence goes the other way around, but for completeness, I like to put it. In this case, again, as Z3, we define X and Y as bit vectors, in this case of 8 bits. Again, I'm using 8 bits in this case because, well, it's kind of simpler. The numbers are more digestible for the human eye, but this kind of transformations work exactly in the same way for any 16-bit, 32-bit, 64-bit, and the functions not because they have to be inverses on the bit size, but the rewrite rules, all of them that we generate are working on any kind of bit size, okay? So we just prove this diagram, as we saw, and just run it. Okay, that's proved, which means that 3 expressions are semantically equivalent, as we wanted to see. So let's discuss now about opaque constants, which is another technique which we can leverage MBA transformations for that all allows us to hide a target constant. So why would we want to hide a target constant? Think, for example, any kind of DRM or, for example, malware that is doing some kind of crypto under the hood. If you have done any reversing at all, usually one of the first things that you take a look is look for cryptographic constants, so you can easily identify cryptographic algorithms being used within the code, so you can trace back where is the yield, what is the data being consumed by the cryptographic algorithm, and so on and so forth. So one of the first things that you do, and there are a lot of plugins for IDA, for Rudder 2, and for any kind of disassembler that actually find you these cryptographic constants. One of the use cases for that is, let's just hide these constants. Let's replace the constants in code by a construction, by an expression that produces the same constant but is completely obfuscated, okay? This construct combines MBA expressions that we'll see in a second with a cool tool, mathematical tool called permutation polynomials. And I will discuss very briefly about permutation polynomials, but essentially a permutation polynomial is just a polynomial, a regular arithmetic polynomial, which produces a permutation which is a one-to-one mapping, a bijection. Okay, which means that we can go from the initial values to whatever the polynomial leads us to, and we can go back because there's a one-to-one mapping, a one-to-one permutation. Okay. In our case, the values that we are using are MBIT values, so it's think of that as a reordering of our box of MBIT values in a way that is one-to-one, which means that we can apply the inverse reordering and get back the original values. Just one note in here. In general, we have that for a permutational polynomial, we want to find that we have another polynomial that defines the inverse. Okay, we have an ordering, so we want to define the inverse ordering. We don't have for granted that this polynomial exists, but we don't have for granted that it exists in the same bit size. Okay, in the same degree, sorry. But such a reordering has to exist because we have our permutation, which is one-to-one, so the other one has to be defined anyway because this is a bijection. So just keep in mind that it might not be defined in the same degree in general, but we will use some permutation polynomials which are nice that have this property, and we can work with them with a pretty bounded degree. Okay. Essentially, this is the definition that we will be using. We want a pair of permutation polynomials, of inverse permutation polynomials. It's called P and Q. And the definition of them is that, well, if we apply one, then apply the other, as they are inverse permutation, inverse mappings, then we apply to some input, we always get the same, as output, the same input as the initial, because one ordering, then we undo the order and we get back the same initial value, okay? In a sense, these functions, these permutation polynomials, are generalization of affine functions. An affine function, you can think of an affine function as a permutational polynomial of degree 1. Okay, these are just the generalization on any degree. So, closing this digression about permutation polynomials, the only thing that you need to remember is that those are polynomials that are inverses between themselves and define a one-to-one mapping. Okay, so we need some MBA expressions, some particular kind of MBA expression that we'll discuss in a second, and also these permutation polynomials. So let's just construct it. What are the ingredients that we need to hide the constant? First, we need the constant that we want to hide. Let's call it K. This is an MBIT constant that we want to hide. Then we need a pair of inverse permutation polynomials. Okay, again, I put again what does that mean, but this is just a pair of polynomials that define one-to-one mappings. And then we need an MBA expression E, which works on any number of variables, we don't care, but that is non-trivially equal to 0. And by non-trivially equal to 0 means that this is an expression on any number of variables, and regardless of the input variables that we throw to evaluate this expression, the output of the expression is always 0. And the non-trivial part just means that this MBA expression is not 0 itself. It's just something that is not trivial, but plugging some variables into it, any kind of variables, it will always produce 0. So it's semantically equivalent to the constant function 0, if you want to think in that way. So now, when we have these ingredients, our constant, our pair of permutation polynomials, and our non-trivial equal to 0 MBA expression, then we can hide our constant by replacing it by the expression produced or the function produced by this construction, okay? This construction is just applying the first one of the permutation polynomials, and as input, it's taking the non-trivial equal to 0 MBA plus the inverse permutation polynomial evaluated in our constant, okay? I won't go over the formal proof of why this actually works, which means that why this construction, the expression that we obtain by this construction, always gets us back our constant. But the moral proof, if you want, is that essentially, if you remove the E from here, you have P of Q of K. And as P of Q are permutation polynomials, inverse mappings, then that will be K. Okay, so we are retrieving K. And why, without being a formal proof, the moral, because we can do that, is because, well, E, actually, their semantics are 0. So the semantics of the expression E introduced within this construction are essentially vanished. They're interleaved within the final expression, but the effects that the E part in here plays within the construction of the expression is vanished because the E, actually, the semantics of E is 0. Okay? The formal proof is a little bit more involved, but the moral of it, like the way in which you can be convinced that this makes sense, is that, okay, you can think that the meaning of the MBA expression E in here, as E is non-trivially equal to 0, is equal to 0 from a semantic point of view, it just vanishes, and then we would have the same meaning as applying P to Q of K, which is the two inverse permutation polynomials cancel one each other, and we get the same constant. Okay? This is a little bit the moral motivation of why this works, while the formal proof is a little bit more involved. We won't go over it. And again, this will be an expression, a function if you want, which will be on the number of variables of the MBA expression. And there can be any number of variables. We don't care because it's always evaluating to 0. Okay? Okay, having this here, let's actually build one. Let's see a practical example of that. So consider, again, working on 8-bit values, again, for the simplicity of the polynomials, I think that we will see, but this will work on any bit size. So consider this pair of permutation polynomials. These are just permutation polynomials, which happen to be inverse. We'll say in a second, but you can trust me that they are inverse permutation polynomials. And then we have this MBA expression, in this case, on two variables, which is a non-trivially equal to 0 MBA expression. You can again trust me, and we will see in a second that this is non-trivially equal to 0. Again, let me repeat. E being non-trivially equal to 0 means that for any x and y values that we evaluate this expression in, the result will always be 0. Okay? But this is non-trivial, meaning this is not 0 itself. So, our task right now would be first, let's check that P and Q actually define inverse mappings, so that we apply one, then the other to give an input for all the possible input, then we receive as output the same as the input. We also check that E, our MBA expression E, defines a non-trivially equal to 0 MBA expression. That means that it produces the 0 output for all x and y inputs. And then let's create an opaque constant using our permutation polynomials that we have seen, and also E to hide the constant k equals 1 to 3, for example. Okay? Let's build this process, this opaque constant function, this opaque constant expression to obfuscate our constant 1 to 3. And finally, let's check that the opaque constant that we have constructed actually works, actually is giving us the constant that we want to hide. So let's do this. First of all, let's check that P and Q define inverse mappings. In this case, I also like to include like brute force method, because we are in 8 bits, we can literally brute force the entire space. You don't really need to read this code if you have it, but essentially I'm defining two polynomials and I am traversing all the possible inputs and checking that for all of them it matches the expected behavior, which is that all inputs produce the same output as the input. Okay, this is brute force. We can do brute forcing here. I want to illustrate that because we are working on 8 bits and it's easy to brute force the entire 8-bit space. If you were working on 64-bit, you can't brute force that in a reasonable amount of time. It's not that you need it, because if you have your permutation polynomials to be correct, you don't need to prove them every time. You already have generated them to be correct. But I want to show you that we are actually working with correct permutation polynomials in this case. So for 8 bits, I said we can brute force everything. If you don't want to brute force, or if you are on any bit size way bigger than that, we can also prove that with an SMT solver really easily. Similarly as we've done before, we import everything from Z3. We define X, in this case capital X, because we want to differentiate, in this case, the permutation polynomials variables from the variables within the MBA expression. So we call it capital X. We just define the two polynomials, and we ask Z3, hey, can you prove me that the semantics of the combination of the two polynomials is equal to the semantics of the variable itself, to the input itself, which is, are those two polynomials inverse mappings? And we just run it, and again, proved. Again, all this code you have it in the materials for today. You want to go over it and play around it. You have all this code available. Then let's do the same thing with the MBA expression E. Let's check that it is non-trivial equal to 0. Again, we can brute force in this case. It's the entire 8-bit space, well, both for X and Y, so it's twice the 8-bit space, but anyway, it's feasible if you wanted to do brute force, which is not something that you want to do in general, but here I want to be super explicit with you. Don't really need to understand anything here. It's just traversing the all possible 8-bit space for the two variables, and then checking that no possible pair of inputs produces a non-zero output, which means all inputs produce 0 output. Okay? Which essentially, in other words, our MBA is a non-trivial equal to 0 MBA expression. Again, we can prove it with Z3, with the SMT. We define X and Y as bit vectors of 8 bits. And then we define our MBA expression as a function. And we ask the SMT solver to prove that the semantics of the expression are equivalent to the semantics of 0. That it produces the same input-output behavior than the constant function 0, that it is non-trivially equal to 0. So you can run it, again, proved. Now, we have proved that we have a pair of inverse permutation polynomials. We have our non-trivial equal to 0 MBA expression. Let's now construct our opaque constant function. This code is a little bit larger, but everything we already seen, like all of that is just copy-pasting what we have seen before. We define the pair of permutation polynomials with capital X to differentiate it. Yep. And then we define X and Y as the variables, 8-bit variables again, for the non-trivial equal to 0 MBA expression. So we have our ingredients in here. We have the pair of permutation polynomials, inverse permutation polynomials, our non-trivial equal to 0 MBA expression, and then we just define a constant value. In this case, we define it as a Z3 object to operate with, combined with the expression. It's just a fancy way of saying, hey, K is a concrete value of 8 bits with value 1, 2, 3. Okay? And then let's just construct opaque constant. Let's just apply the definition of the opaque constant, or opaque constant function, or opaque constant expression was the polynomial P and the input for it being the MBA expression plus the polynomial Q, its inverse, applied to the constant K. Let's just do this construction, and then let's print it. Here I have a kind of simplified function which comes from Z3, which in a way the only thing that it's doing is grouping the terms together and collapsing the constant that might be laying around. It's just a way of printing a little bit nicer, okay? But it's not doing anything else, just printing a little bit nicer. So we create this opaque constant, we run it, and this is our outcome. This is the expression that defines the opaque constant, which means this expression on X and Y variables, on two inputs, on two 8-bit inputs, always produces as an output the constant 1, 2, 3 for any values X and Y. This is our opaque constant function. Let's check it. Again, we can brute force the entire space for 8 bits. This is not something you can do in general for bigger bit size, but in this case you can do it, and I want to be super explicit. So we just define our function. Here's exactly the same function, put a little bit more compacted, so it fits in the screen. And then we iterate over the whole 8-bit space, and we check that there is no possible pair of inputs that produces a result different than 1 to 3. So we just run it and say, okay, your Opaque constant is 1 to 3. We can also prove that with an SMT solver. Again, the same thing that we've done so far. We define x and y as bit vectors of 8 bits. We define our Opaque constant function, and then we ask the SMT solver to prove that our Opaque constant function is semantically equivalent to the constant function 1 to 3. Okay? We just run it, it's proved. Which means that this function now, we can use it in our code, in our C code, or anything that we are using. And instead, well, here is 1 to 3, where it can be, for example, all the MD5 constants that you want to hide that you're using MD5 for whatever you might be wanting to use MD5. Instead of having the constant lying around in the data section of your binary, you can have calls to functions which are obfuscated with random parameters calling these functions. And also, you could also construct like 10, 20, 30 different functions using different permutation polynomials, different and non-trivial equal to 0 MBA expressions for the same constant. And every time you need that constant, you call a different function kind of randomly. You can pick whichever of them, and you can use kind of also random inputs for any of the functions that you wanted, and you will get back the constant that you want. Okay? So, well, just some words before the summary. You might be thinking, okay, but if I'm doing dynamic analysis and I just see this function and I try to run it like several times or even with an emulator, I will see that it's always producing the same output. And the answer is, yeah, of course. But that's not immediate. For an analyst, for an attacker to get to a point where you have isolated a function or a set of functions that you think they are suspicious, and you decide, okay, let's try some probabilistic approach. Let's try to run or emulate that a lot of times to see what happens, and then discover, okay, it's just a constant function. First thing is that is not immediate. It requires some degree of malware analysis and understanding of the whole program, which can be obfuscated as well, to be in a position where you can say, okay, let's just take a look at this and then decide that it's constant. But even if we're in this scenario, there is some ongoing research, which is, as far as I know, there is no public research on that, but at least I know another person doing kind of similar things, apart from me, where we can construct these kinds of things, but they only produce the constant desired if x and y, they are not some specific values, but they satisfy some kind of constraint. So, for example, I have some private research that I hope to publish soon, where I can construct these kind of things, but only when x and y can be seemingly random, but they have to satisfy that x and y are inverse integers modulo the bit size that we are working with, for example. So it's even more resistant to this kind of dynamic emulation analysis for probabilistic approach, because the true constant would only reveal on some certain cases for some constraints, and for other kind of inputs, it will produce seemingly random output. So there are some improvements that can be applied to that. There's some research ongoing, but this construction by itself, if combined with several functions for several constants and just picking randomly and using random inputs, it's very, very effective, especially to thwart a slowdown of the analysis and the detection of maybe some crypto constant being used, or maybe some part of some keys for some decryption of some assets or whatever. Okay? So, as a summary, we've seen how to apply several MBA obfuscation techniques. In particular, we have discussed about MBA rewriting, insertion of identities and opaque constants, and to do that, we have used several tools, in particular, rewrite rules. We have introduced find functions, permutation polynomials, also these non-trivial equal to 0 MBA expressions. Okay, so now I want to do a bit of demo about, okay, this is cool, but what can we do with that, like in real life? If I have not convinced you enough with the examples that I gave you that this is really powerful, we can see not very advanced examples, but some real examples about it going on. Okay, let's go back to here. So we have some time to play with it. So, can you read that well from the back? Okay. So imagine that you have this super dumb code, this function, which is just, okay, we receive 2 parameters from standard input, and we generate an XOR and print it, the XOR result of that. Okay. So we take a look at the assembly of that. Well, actually, let's just, this is the main function and everything is in there. And if you see that practically all of the code is parsing the standard input and converting into integers, okay? So there's nothing going on in there. And then when we have that, the only actual semantics happening here is, okay, we have the first parameter, the second parameter, and we are doing an XOR, and then that's it. Let's print it, and we have finished. There's nothing fancy going on in here. Just loading the parameters and doing this XOR, which is kind of stands out immediately. What if we just want to have this kind of functionality, but we want to mess with, in this case, with the control flow, with what is actually doing the code. So we can use MBA transformation and this kind of expression that we have seen to obfuscate the control flow by means of producing opaque predicates, okay? Let me explain you in a minute what an opaque predicate is, but essentially an opaque predicate is a conditional statement, a conditional expression that it is always known to be either true or false. So the person doing the protection or putting the code knows a priori that this condition will always hold true or will always hold false, but it's not trivial, it's not apparent at all. And we can use this to put essentially fake branches in our code. We can use fake branches on conditions that they will always be true or will always be false. So some of the branches will never be taken. So this will mess the control flow by means of producing this kind of conditional statements. And we can build some of them actually with MBAs that we have seen. For example, we have here 3 different MBAs. Actually, some of them are from the examples that we have seen. So the first thing, let me just put some spacing here so it's easy. So the first thing I have in here is like, okay, this expression, which is, if you remember, the first right rule for the addition, is equivalent to the second. This is what we obtain through the insertion of identities to the addition example for the obfuscation. So these 2 actually are 2 different representations of exactly the same semantics, which indeed is the addition of the 2 variables. But we just have that these 2 things are semantically equivalent. So if we make a branching of comparing these 2 things, we know the outcome. It's not trivial at all, but we know the outcome of any branching, any conditional statement involving these 2 expressions because they are equivalent. Okay. Same thing happens here. So this is a non-trivial equal to 0 MBA expression. So if we do any kind of conditional statement with this, using this nonlinear MBA expression, we know a priori what will be the outcome because it's equal to 0. So anything that we compare it against, which is not 0, will be always false. Okay? And then we have this, actually, the opaque constant that we use. This is another conditional statement that is always true. This expression is always 1 to 3. So any kind of conditional statement that we build with this knowledge, we will know its result, its truth value a priori. And we can actually build that. Fairly simple. I have here, for example, from the first example, I just construct, okay, this expression is greater than this other expression. So I have just an if statement of, okay, if this expression is greater to this expression, like if the evaluation of whatever the value that we get from x, plugging x and y in this expression has to be greater than plugging x and y in this expression. But remember that we know that these 2 expressions are semantically equivalent, so this will always be false. But the person analyzing the binary resulting from that doesn't know it. That's the whole point. Then we are checking, for example, that the second expression to be exactly equal to 0x17. But we know that this MBA expression is non-trivially equal to 0, so it will never be as OX17. So this branch will never be taken again. And this is, okay, the last one in here. This using the opaque constant construct, you see that it's not always that we can use it to hide the constants themselves, but you can then do smart things to use this kind of knowledge, this kind of constructions. We say, okay, this whole expression until here, minus 57, because yes, it's less than 100. So we have that this whole expression before the minus 57 is equal, semantically equal to 123. So 123 minus 57 is always less than 100. So this conditional statement is always true, regardless of the x and y conditions, because we have constructed it in a way that we have a semantic meaning of 123 obfuscated minus 57 is less than 100. And these are fairly simple conditionals because this 57 could be another opaque constant construct, the same for the 100, and here we could have a lot of more obfuscation going on, a lot of iterative rewrite rules, okay? And then, in this case, okay, we do the XOR, which is the actual semantics of the code that we're trying to obfuscate, and else we just z equals 0, but this will also never be taken because we will always go here. This code will always go to this line of code. It will never reach any other of the branches because we have opaque predicates that introduce fake branches in the code, essentially to mess around the control flow, okay? And again, this is fairly simple, and I only targeted the control flow, but you could also obfuscate these expressions by themselves. So even if you arrive here, then you might not see that this is an XOR because this is an XOR that has been obfuscated, for example. We are not doing that here. We'll do it in the next example. Okay. But let's take a look at the assembly representation of that. I think I have it here. So now we go to the main. Yeah. This is the control flow graph representation of it. So before we just had a single basic block, and now we have not a lot of that, but a little bit of branching. You don't really know at first sight what is going on in there. And actually, if you go to the branching conditions, for example, now to this branch, you see the coding here, okay? It's not clear what's happening. We see that the comparison with 0x17 and then the branching condition depending on that, but we are comparing against 0x17 the result of all these computations, which is not clear at all what's happening in here. It is not clear at all that this produces a computation which is non-trivially equal to 0, okay? And the same thing for the other branch. This actually goes even beyond that. There's a lot more code in that. And yeah, for the rest one, this is, okay, we are at the last branch, this is the return 0, that we will never take this branch because we always had the other branch being taken, which is exactly this branch, which is the only one that will be taken always. This branch will always be taken because all the rest of the branches are fake branches introduced by the opaque predicates, okay? And these are just an XOR, very simple, but we could also obfuscate all the actual semantics of the expression being executed regardless of the opaque predicates, okay? In this case, we just plugged into opaque predicates to make it a little bit more simple for the example. And again, this is just 3 opaque predicates, but there is malware around that is using a lot of different opaque predicates to obfuscate a lot of their functions, their components, and they can be extremely big control flow graphs. This is a very simple control flow graph, but you can imagine a control flow graph of like thousands of opaque predicates, so it's kind of impossible to follow the flow of the code in an intuitive manner at all, okay? This is just very simple from one single basic block to a few branches, but you could do that you could go as big as you wanted. Okay. Let's see now a little bit of how can we apply it to harden even more virtualization obfuscation, and let me walk you a little bit about virtualization obfuscation in case you're not familiar. But essentially, okay, imagine that we have this function and we want to obfuscate it, okay? And now we are not going to obfuscate it now, the expression itself. we're going to build a virtual machine obfuscation for that, and then harden the virtual machine, okay, to see that we can really go to state-of-the-art obfuscation in that. What does it mean to, what is exactly virtual machine obfuscation? You might be familiar with things like VM Protect or Themida, or even the Nuvo VM for video games, which are hard protection, or in theory hard protections, which essentially what they are doing is transforming the code that wants to be protected, all the code that they want to protect, or the function they want to protect, into a custom-made architecture, into a custom architecture, totally made-up architecture that they design, that can be designed kind of dynamically. And this architecture is an architecture of a virtual machine, of an abstract machine, totally made up, which has some opcodes and some instructions and works in any way. So what we do with virtualization-based obfuscation is we translate the function or the code that we want to obfuscate, we translate it to the bytecode, to the machine code of our abstract machine that we have designed. And then within the code, what we do is instead of calling the native function, we call an interpreter for our custom VM, or an interpreter for our custom machine that will parse the bytecode, the machine code, representing our code that we wanted to obfuscate. This might be a little bit confusing, but this code you also have available, and it's a very simple VM implementation, obfuscation VM implementation, and let's walk through that. So essentially, in this demo, I want to obfuscate this expression with a VM, okay? So the first thing I will do is, okay, let's just invent, totally made up, a custom architecture with some operators so we can translate this expression into our virtual machine. So I did that in here. This is our virtual machine, like our interpreter for the virtual machine, which essentially the only thing that you have to be interested in is that, okay, I'm going to define that the opcode A0 will be a push. The opcode B0 will be a pop. 1-0 addition, 2-0 subtraction, 3-0 multiplication, 4-0 XOR, 5-0 AND, and the last one, 6-0 OR. So we will have these opcodes, these instructions in our virtual machine, okay? And then we define, we have designed a virtual machine, an abstract machine with these opcodes, and we want to transform our code that we want to obfuscate into bytecode, into actually machine instruction for our abstract machine. In this case, here you have the bytecode representing the function that we want to obfuscate with all the comments. So this is the bytecode that represents in our virtual machine, which happens to be a stack machine. And the only thing that means is that we will have all the operation going on in the stack. So we will have push a value, this will be 4, this will be X, then push another value, then addition, push, variables, and pushing variables or XOR submultiply. And this is exactly the semantic representation of our function, but within our VM. Because what it's doing that, first of all, we push 4, we push X, we push Y, and the first thing, well, this is a stack machine, remember, we are an addition. Okay, what will do the addition instruction? Will pop the two previous pushed values and add them together. See that this is exactly the first thing that might happen from the inside out in here. We are evaluating from the inside out, from the parentheses. Actually, I have put in here the postfix representation, which is the native representation for a stack, if you want to think it that way. This is just the notation for the reverse police notation, stack notation, postfix notation, however you want to call it. So this is just pushing variables, and then every time we have an instruction, then we pop the two previous values and apply the instruction. So then the bytecode representing the instructions for the expression that we want to obfuscate in our totally made up virtual machine is this bytecode. So this is our machine code for our custom made virtual machine that will execute it. So what we do, instead of calling our function in the native architecture, is we will call an interpreter for this virtual machine passing as an argument our bytecode. So we will call an interpreter of our virtual machine that will interpret the bytecode that represents the expression that we want to obfuscate in this virtual machine. And the interpreter is just a loop with a switch case. Nothing more fancy than that. We have it in here. This is just some syntax sugar to see where am I traversing the bytecode array. And then, well, let's just get the current bytecode instruction. Let's make a switch for the current instruction. If it is an A0, then this is a push. Otherwise, this is a pop. Otherwise, this is an add. This is a sub. And all these functions are implemented in here. Okay? We have push and pop, which are kind of special in this sense. We have a stack. And then, for example, with addition, the only thing that does is, okay, I'm going to pop from the stack the operands. The result will be applying an addition to the two operands and then pushing the result back to the stack. And this is the same for all the instructions, okay? This is how we build a very, very basic virtual machine obfuscation. Why? Because now our code won't be this expression being evaluated in x64. It will be an interpreter interpreting some bytecode of a totally made up instruction set. Okay? This closes a little bit the digression of the virtual machines, and if you are still a bit confused about VMs, don't worry about it, because what we will do with MBAs is just making the VMs way harder to understand, to analyze. So, what does this look like in assembly? So let me go straight to the interpreter. Okay. This is the interpreter, okay? The control flow graph of the interpreter. Let's just see a little bit of code to make it somewhat more digestible. Not here. Here, for example. Here. Okay. The first thing that's happening in the interpreter is we are comparing, essentially, this is the instruction for the bytecode, okay? You don't really have to care about these details, but what is interesting to see is this set of comparisons. We are just comparing some variable, which in this case is the current byte of our bytecode, with a value. And if this value is okay, then we will go here. In this case, this value, B0, is the opcode of our bytecode representing the pop instruction. So we go here, and I left the push and pop calls to be explicit calls to make it a little bit easier to follow, but they could be also inlined. Then, okay, let's just keep push and pop, and I'm interested, for example, in this one. This one is interesting. So, compare the current bytecode with 0x60. This is the switch. This is the switch implementation that we saw. So, if it's 0x60, then we'll go here, which will essentially, as we discussed, pop the two values from a stack and then apply this OR. You see this OR? This is the semantics of this handler. This is called a virtual machine handler. Okay? This is the semantics of this instruction of the virtual machine. And even if it seems super cumbersome, we can quite easily, I would say, analyze such a virtual machine by means of just locating the bytecode, seeing where each instruction of the bytecode goes, and observing what is the semantics, what is the behavior of each bytecode. So we could say, okay, for OX60 represents the OR operation. And we can see the same happening for a lot of the different ones. For OX50, we have the same, popping the two values from stack, and we have an AND operation. Okay? So in this case, it's fairly simple to actually build a kind of, with some scripting here, with either Python, with R2Pipe, with whatever you want, just traverse this, hook each comparison, check what is the value of the bytecode bit compared, go to the truth branch, and check what is this instruction after the pops that is being executed. So we would say, okay, 0x40 is an XOR, 0x50 is an AND, 0x60 is an OR. So we could construct our kind of disassembler for our virtual machine. And this is roughly the way that we can analyze virtual machine obfuscated code. So what I wanted to talk about virtual machines, and not because I like them, that I do, but this is a very, very bare bones design of a virtual machine where it's very easy, once you have abstracted everything from the virtual machine, it's very easy to see, okay, this 0x40 is related to the semantics of an XOR. So the 0x40 opcode of the instruction of the virtual machine that I am analyzing actually represents the XOR. So you can actually build this kind of mapping between the opcodes and the instruction, and then reconstruct the behavior of the virtual machine and essentially get back what is the semantics that are describing, what is the behavior of the code that is being virtualized, that is being protected with this kind of virtualization, okay? But what happens, and here MBAs play a role, and software protection mechanisms are starting to play with these things a lot more and more, which is, yeah, but what if we had kind of the same construction, but here we don't know what's happening. Here, this XOR or this AND is not clear at all what's happening, because here it's crystal clear. Once we see this branching, we see what is the opcode being compared, and we see then exactly what is the operation being performed by that instruction. But can we obfuscate this extraction? So can we actually obfuscate beyond the virtual machine obfuscation itself? We can also obfuscate the semantics of each instruction of our custom virtual machine. So it's even more complicated to reason about it, because even if we understand that we have a virtual machine that is doing something, and we have some handlers, some instructions for a virtual machine, then we need to understand what each handler is doing, what is the semantics of each of the handlers, each of the virtual machine instructions, so we can reconstruct the behavior of the obfuscated code. And in this case, it's very simple to do, because we have it like in clear. The instructions pop up at first sight. So again, this is the XOR. We have another more here for the 0x30. This is a multiplication, and so on and so forth. For the 0x10, this is just an addition. Just popping the two values and applying the thing. So we could reconstruct kind of a disassembler for our virtual machine, because we have understood very, very clearly what each of the opcode maps in terms of instruction, in terms of semantics. So what can we do with MBAs? Make it even more complicated by means of not making it obvious or not making it easy to understand the semantics of each VM handler, of each handler of the virtual machine. How do we do that? Well, I have here some rewrite rules. These are rewrite rules for the addition. This means that op1 plus op2 is semantically equivalent to this other expression. Op1 minus op2 is semantically equivalent to this other expression. The same for multiplication, XOR, and OR. Okay? Again, those are fairly simple obfuscation expressions. I'm using kind of simple and a small one for the sake of, well, putting them kind of nicely in the screen and making it not so terrifying. But these expressions could be as long and as complicated as you want it. And you can generate them arbitrarily complex and arbitrarily long. And then here we go into a discussion, if you want, that usually when you're protecting software, there is some kind of compromise between how many computing cycles are you allowed to waste on some functions for obfuscation. So how far can you go in obfuscation within the constraints, the performance constraints that you might have. But this is another discussion from the point of view of how big can you go in obfuscation. With MBA transformation, you can go as big as you want, because you can just keep applying rewrite rules iteratively and in function identities, and you can just make it bigger, 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 and bigger until you want to stop. Okay? So anyway, I have generated these expressions, and well, let's just take a look at what a virtual machine in this case might look like. And the only thing I did in this code is everything is exactly the same, but for the functions that define the semantics of each handler, of each opcode, the functions which are the VM handlers that define the semantics of each opcode, which means the function that defines Well, again, push and pop, I leave it as is, so it's easier to follow. But for the addition, subtraction, multiplication, XOR, and the different instructions, these functions, instead of having simply, as we had here, okay, popping the values and then doing the result straight away, I just put MBA transformations that obfuscate that. So in this case, so see that. The addition now is this set of operations, the subtraction is this other, the multiplication is this other, and so on and so forth for the rest of them. Okay? So we can now take a look at the assembly of that and observe that now it's not that easy. No, not main. Let's go directly to the interpreter. And now we see the opcodes. For example, here, the 60, remember. Then here, we have the two pops. The first pop is about, and then here, and then we have something in here which is not clear what's happening. So we cannot build a kind of easy disassembler in this sense for any of the instructions. Let's see some more. Here, for example, we are comparing with 50 again. So we can say, okay, I have the 50. Let's see what is the semantic, what is the instruction that is encoded in this virtual machine. We don't know. You don't know from here what's happening. Because an obfuscation transformation, an MBA transformation that obfuscates the semantics of the original VM handler obfuscated code, okay? I know this VM example can be a little bit tedious and hard if you have no exposure at all to VMs, but what I wanted to introduce is that we can use MBA transformation to harden even the kind of the most advanced techniques, even if this VM is very toy VM for the sake of the demos. But any commercial VM protection, the basic idea is the same. Build a custom VM, transform the code that you wanna protect into bytecode of this custom VM, and then run it within the interpreter of this custom VM. But we can obfuscate a lot the possibilities of kind of quickly understanding what each of the bytecode opcodes translates to in terms of semantics by means of obfuscating the semantics of the opcodes of the handlers themselves for each of the instructions of the VM. Okay? Yeah, I think that's kind of everything for the demos. We have some time, but let me just give some words before. So you might be thinking, yeah, all that is super nice, but well, how the hell do you generate all the things that we need? Okay, so we like what would come next would be learning methods to get the tools that you need to generate this kind of transformation. So for example, we need methods to generate non-trivial equal to 0 MBA expressions. So I have given you a couple of them on the slides on the code, but you might want to generate your own non-trivial equal to 0 MBA expressions, so you can play with them. Also, linear MBA rewrite rules, and I say linear because, well, the method that we know to generate rewrite rules essentially generates linear MBA rewrite rules, which then we can make non-linear by applying identities of functions as we've seen, but the method itself is just linear. We won't go over it right here, but there is published material and I have references for that, and you can ask me without any problem after the conference. Mainly because that would be like an entire day discussing these methods. Okay, but just to give you some ideas, we have a method to generate non-trivial equal to 0 expressions. We construct some matrices, do some computations, solve some system of self-equations, and we generate these non-trivial equal to 0 MBA expressions. And then from that, we have linear MBA rewrite rules for free. Because the only thing that we do now is, okay, we have a non-trivial equal to 0 MBA expression. Let's just move things around the equality to generate rewrite rules. For example, let me get back a little bit and explain that with, I think, come on, this. Here, for example, we could have we could generate from this non-trivial equal to 0 MBA expression, we could generate a rewrite rule for the XOR, for example. You could put XOR, like move it around, changing the sign, and then X XOR Y would be this thing. A rewrite rule for X XOR. And similarly for X minus Y, you could move everything else, changing the sign to the other side, and get a rewrite rule for the subtractor. So once you know to generate a non-trivial equal to 0 MBA expressions, then rewrite rules come kind of for free. Okay? It gets back to where we get here. So these two things. We have a method to generate this. In all the reference that I will point you, you have this method. It may be a little bit complicated to understand or to program. I have code for that, which is not public, but if you can ask nicely, I can share it. And then we would also be interested in generating, well, both pairs of affine functions in general, in particular, well, affine functions are in general permutation polynomial, which, as I've been mentioning, an affine function and affine mapping is just a permutation polynomial of degree 1, okay? So we'd also be interested in generating this kind of stuff. I can also give you some words for that. For affine functions, it's very simple. Just Google affine cipher, which is not the same that we are doing, but the affine cipher is just classical cipher that uses affine functions and actually uses inverse affine functions that you have the description of how to get from an affine function to its inverse really easily. So there is just one constraint, which is that the coefficient for the x has to be odd, and then you can construct its inverse very, very easily, okay? It's everywhere. This method is everywhere. For inverse permutation polynomials, it's a little bit more complicated. There is a method, which is on one of the references that I will give you, that allows you to produce inverse permutation polynomials of the same degree, but it's a method kind of limited in the sense of it imposes a lot of restrictions on the kind of permutation polynomials that you can generate. So the space of permutation polynomials that you can generate is way smaller than the space of the whole permutation polynomials that will allow such an inverse. But publicly, it's the best we have so far. There are some research papers recently that introduce methods to generate pairs of inverse permutation polynomials on any degree. So for example, a permutation polynomial of degree 3 might have an inverse permutation polynomial, but which is in degree 17, I don't know, which might work for you. I mean, there's no problem that they have different degrees. Just if you want to have it bounded, then the method that we know so far is kind of limited in the permutation polynomials that you can actually create. There's some private research that I'm aware of, especially because I've done some of it, for actually doing general generation of inverse permutation polynomials of the same degree, which is way more general and can cover all possible permutation polynomials. But it's not finished. I have some partial results, which are great for some small degrees, and I hope to have some more time to play into that. But until then, there are methods to do that. The ones that have the same degree is a little bit limited because you have a small number of permutation polynomials that you can generate, and there are other methods that can give you, in general, any kind of inverse, but you might not have bounded the degree, which is something that might be interesting depending on the constraints that you have. So, this is a little bit about the talk. Some references. This is, the first one is a shameless self-plug. This was my PhD thesis from a couple of years ago. Actually, I have another thesis after that, which is not linked in here because a little bit I go into things that I have not covered really in here. But here, there is a lot of MBA explanation. Here, there is a lot of MBA explanation. Actually, this is really nice. This is a PhD thesis that reads kind of easy. Don't be worried about the PhD thingy. It reads kind of nicely. And then this is the paper, which was like the first paper that introduced this idea of mixed Boolean transformation for code obfuscation. This is from 2006, I want to think, 2007. No one cared about it until more than 10 years later. Then people started to say, hey, this is really interesting, and we can use that for obfuscation. And then from the other side, people said, okay, so we want to address that to the obfuscate to be able to reason about it. And that's what has been motivating this kind of research appearing like super recently. So it's like 5 years to now that people have started to research a little bit seriously on this kind of thing. So there's a lot of things to be done. So these references, and all the materials, this is, if you scan that, you go directly to my GitHub with all the materials for today are already uploaded. You have the slides, the demos in the slides, and all the code that I have shown. And, well, you can check everything if you want. If you don't catch the QR, don't worry, I will tweet that. I will upload it to the Hack in the Box repository as well. And also, if you just go over my GitHub, which is the same handle as everywhere else, on the pinned repo talks, you can find it. So if you're interested, you will find it. That's no problem. And that's a little bit about me. I would love, if you want to get in touch, you're interested in that, you want to discuss more, I will be probably around today, but for any kind of inquiry, anything you're researching, any issue, any cool idea that you have, you can get in touch with me. I'm mostly on Twitter, Arnau Gàmez, but you can find me on Discord, Telegram, mail, wherever you find me. And also on, well, my website has also contact information, the website of my security firm, where, well, I offer trainings and other kind of consulting on obfuscation, deobfuscation, software protection, and this kind of thing way more extended. If you might be interested in that, it's also cool to check it out. And that's it about me. It was a pleasure being here at Hack in the Box again, in person again. And I wanted to thank all the organizers and the crew, the video guys that are putting this together really nicely. And it's been really happy to be here again. Been here for a few days already doing my training the previous days now. I really wanted to do this free lab session for everyone being interested because it's kind of a niche content, but people who are interested, I'm super happy with sharing and discussing anything with them. That's it. I think we have a few minutes if you have some question. Otherwise, I'll be walking around. You can always find me on the internet for anything you may need. Thank you very much.